So after talking about the Snell's law and refraction at plane surfaces, we now move to refraction at curved surfaces, and we look at the simplest and the most intricate of all curves, a sphere. So we look at spherical surfaces and how they refract light, and we will do this in many different cases. All have the same idea behind them, but they have different a bit different mathematical proofs. You can dive into all of them or just take one and do the rest as exercise. Let's start with the most general one. So since it's a spherical mirror, it would make sense to first get a sphere. So if I draw a sphere like this, I guess that's fine. Now, what I do is I first find the center of the sphere. So let's say this is the center. And I put my object right here. Let's say this right here is my object. I now draw a line between these two, connecting the center and the object. And I call this my principal axis. So this line right here, the prominent one that you see right here, I'll call this my principal axis. Now, on this principal axis, we can name a few points. The point where the principal axis intersects the spherical boundary, let's just call this point P after pole. Let's say the center is called C for center, and let's say the object is at point O. Now, we now have refraction of light rays. So let's take the first really trivial light ray, and that one is the ray OP. So wait, let me undo that one. So the ray OP, so it goes like this. Now notice that through this ray goes undeviated. If you notice carefully, the normal at this point, the normal to the surface at this point, the interface, the normal looks like, the surface looks like this, and the normal itself is actually just this line right here. So the angle of incidence, that is equal to 0. That implies that the angle of refraction is also equal to 0. So this line passes on undeviatedly. That is one tiny trivial example. Now let us take a ray that is slightly above the principal axis. So let's say it goes something like this. So this is the second ray that we are taking, and in this ray, let us say the line joining, oops, again, I did the same mistake, pardon. In this ray, oops, I accidentally deleted everything, sorry. This was the ray, and now we connect this point where it intersects the surface to the center. Why? Since this is the normal that we are taking into consideration. This is the tangent to the surface, and that is what we represent the interface as. And this is the normal. The brown line is the normal, this one right here. And since it is refracting, let us now take some refractive indices. So let us say that the outside region, for the sake of the argument, let us just say this air, or any medium for that matter. Let's say that this is a medium of refractive index N1. And let us say that this sphere, this is a medium of refractive index N2. Now, we're assuming that N2 is greater than N1. You can try another variation of this as you may like it. Now, since N2 is greater than N1, the angle of incidence, that is going to be greater than the angle of refraction. So the angle of refraction is going to be actually smaller, and the ray would deviate something like this. So let's say the ray intersects the principal axis inside the sphere, right at this point. Let's say that that point is I. Let's label this angle as R as well. First things first, let us first write the Snell's law right at this point. So Snell's law would tell us that n1 times sine of I, that is equal to n2 times sine of r. So this is something that will help us in the future. What else can we write? Well, we can now start relating angles and distances. That is something that we'll be doing consistently throughout geometrical optics. So let us assume that this angle right here, let's say that this angle is, this angle is alpha. Let us say the angle this line makes, the image line ray makes with the principal axis, let's say this is beta, and let us say that this angle is theta. What else can we do? If you notice carefully, in all these triangles, let me just name this point as Q. So in all these triangles, whether it be QOC or whether it be QOI, whether it be I don't know, QCI, all of these triangles have the same height, and that height looks something like this. So this is the height of all of these triangles. Let us say the height is nothing, just the perpendicular that we drop from Q onto the principal axis. And let us say that this meets right here at some point M. Now, what else can we do? Well, since we have angles and we have distances, we can measure these distances experimentally, we can start relating them using trigonometry. So we know that this distance OP, this is the object distance. This distance is the object distance. The distance PI, well, that is the image distance. The distance PC, that is the radius of curvature. Now, since the right angle in this figure, in the figure that I have grossly misrepresented, since this right angle is at a point M that is really, really far away from the pole, it doesn't really make sense to approximate things here. So instead, let me draw a better figure so that we can at least get some feel of how approximations can be made right here. So I'll just quickly redraw this diagram here again, just to make sure that M actually lies close to P, so that approximations really just make a bit more sense. So this is a zoomed in view, and we have this ray coming in right here, and we have this ray going right there, and we have the radius right here, the radius length. This is Q, this is C, this is I, this is P, this is O, and this angle is theta, this is beta, this is alpha, and let's say it's not much better, but still, this is better than this. PM has to be minimized as much as we can. Why? Because the angles that we are making are really small. The aperture is really small. So in order to approximate, in order to use the holy grail formula of optics, that is sine of theta is equal to theta, we need to ensure that theta actually looks small, or to get a feel for it. Anyways, let us say, or also the other angles. So this angle right here is R, and this is I. We now write that this distance QM, that is equal to h. That's just a mere assumption, doesn't really have to do anything with the physics involved here, or the math. Math is more involved here. We can start writing I and R in terms of these angles. Why? Because we can write tan of alpha as h over OP. We can write tan of theta as h over, actually it is OM, since this is the distance we will take. And we can write tan theta as h over cm. We can write tan beta as h over im. But again, as these angles get closer and closer to 0, alpha and beta, we can see that this distance pm, as that goes to 0, OM will almost be equal to OP, which actually happens to be the object distance. CM will almost be equal to CP, and similarly IM will almost be equal to the image distance, IP. So since the only one formula that we know, anything new that we know, any physical formula that we knew is the Snell's law. Again, this is refractive index n1, this is refractive index n2, and since that its statement is something like this, and the angles right here are I and R, it will make sense to formulate I and R in terms of these angles that we can relate with actual distances. So right off the bat, angle I is the external angle in triangle OQC. An external angle is just the sum of the other two angles. So I is equal to theta plus alpha. The other angle, angle R, you can notice it here. Notice it in the triangle QCI. In this triangle, theta is the external angle, and theta is equal to R plus B, and that gives you R is equal to theta minus B. Take both of these and put it right here. That now gives us n1 times sine of theta plus alpha is equal to n2 sine of theta minus beta. Now again, we again say that these angles are really, really small. So we say that theta is almost tending to 0, alpha is almost tending to 0, beta is almost tending to 0. So it will make sense to right away apply, again, the holy grail formula of geometric optics, sine of theta is equal to theta. So that will give us n1 times theta plus 1 is equal to n2 times theta minus beta. Sorry. Now what do we do? So this is a relation purely in terms of angles. Let us now change this into a relation in terms of distances. So we again come back to these equations right here that relate tan of the angles with the distances, and we have been using sine of theta is equal to theta, approximately equal to theta. We can also use the other formula that relates with it. I keep using on this ugly pen. The other formula that goes in hand is that tan of theta is actually almost equal to theta. So instead of alpha, we can say that alpha is approximately equal to h over OM or h over OP, since this is also another approximation that we made. H over CP right here, theta is approximately equal to h over CP, and beta is approximately equal to h over IP. So let us just put that in right away. So n1 times theta is h over OP, so h over OP plus alpha. Theta is CP and alpha is OP, my bad. CP and h over OP, alpha is h over OP. This is equal to n2 times, again, theta is h over CP minus beta, the angle beta is h over IP, h over the image distance. Let us cancel the h's, and once you do that, we can quickly notice that there are two CP terms. Let us just write them in one place. So n1 over OP plus n2 over ip is equal to n2 minus n1 divided by cp. What else can we do? This is a nice equation, but in order to get a more general equation, and you will appreciate the generality of this once you derive it for other cases, is when you put it and plug this in with sign convention. What is the sign convention? The sign convention that I like to use is that in the direction of the incident ray, which is this direction, all distances measured in this direction, in the greenish direction that I just draw, all distances measured are positive. So if that is the case, then the distance OP, the object distance, well, that is measured opposite to this sign convention, so it has to be made equal to minus u. So OP is equal to negative of u. IP, on the other hand, well, that is just in this direction we want it to be, so that is equal to positive v. CP is again in this same direction, so that is also equal to plus r, the radius of curvature that we wanted. This gives us finally n2 by v minus n1 by u is equal to n2 minus n1 by r. This equation right here will help us at all instances whenever we have any refraction at spherical surfaces. There are a lot of assumptions that we used. We used the fact that p is very close to m. We used the fact that angles are really small. We used the fact that when angles are really small, tan of theta, and sine of theta, all of them are almost equal. But in real life, this equation almost certainly gives a pretty good result, at least one that can be worked with, and we will continue to see its applications. You can try deriving this for other situations, or you can watch more derivations in other situations as well. See you in the next video.